Welcome to this session where we'll solve LeetCode problem number 1295, titled Find Numbers with Even Number of Digits. In this problem, we'll explore how to efficiently determine the count of numbers in a given array that have an even number of digits. Let's dive in. The problem asks us to determine how many numbers in a given array contain an even number of digits. For example, if the input array is 12, 345, 2, 6, 7896, we analyze each number to count its digits. The number 12 has 2 digits, 345 has 3 digits, 2 has 1 digit, 6 also has 1 digit, and 7896 has 4 digits. Among these, only 12 and 7896 have an even number of digits. Hence, the output in this case is 2, because there are 2 numbers with an even digit count. Another example is when the input array is 555, 901, 482, 1771. Here, 555 has 3 digits, 901 has 3 digits, 482 also has 3 digits, and 1771 has 4 digits. Out of these, only 1771 has an even digit count. Therefore, the output for this input is 1. Additionally, consider the input 0, 1, 10, 100, 1000. For this example, 0 has 1 digit, 1 has 1 digit, 10 has 2 digits, 100 has 3 digits, and 1000 has 4 digits. Among these, 10 and 1000 have an even number of digits, so the output is 2. To summarize, the task is to count numbers with even digit counts in the array. The constraints specify that the array length can range from 1 to 500 and the values in the array are positive integers between 1 and 100,000. A key observation is that numbers with even digits have digit counts divisible by 2, such as 2, 4, or 6. It's also important to consider edge cases, like arrays with only one number, arrays where all numbers have odd digits, or arrays containing the smallest and largest possible values. These conditions ensure comprehensive handling of the problem. To solve the problem of finding numbers with an even number of digits, we can explore several approaches. The first is the brute force approach. Here, the intuition is to convert each number into a string, calculate its length, and check if that length is even using the modulo operator. This involves iterating through the array, converting each number to a string using the str function, and then using len to find its length. While this approach is straightforward and easy to implement, it does have some trade-offs. The time complexity is O, n asterisk k, where n is the size of the array and k is the average number of digits per number, as the string conversion and length calculation take time. The space complexity is O, k, as we need to store the string representation of the largest number. Although simple, this method can be less efficient for larger inputs as it involves string manipulation. Another approach we can consider is the mathematical method. Instead of converting numbers to strings, we can use division to count the digits. By repeatedly dividing a number by 10 and counting how many divisions are needed until the number becomes 0, we can determine the number of digits. This method avoids string conversion and is more efficient in terms of space, but it still requires multiple division operations, which can become computationally expensive for very large numbers. Now, let's examine the mathematical approach in more detail. The time complexity remains O, n asterisk k, where n is the size of the array and k is the number of digits in the largest number, as the digit counting loop iterates k times for each number. The space complexity, however, is reduced to O1, since no additional data structures are needed. This makes it more efficient compared to the brute force method. However, repeated division still has its downsides, especially for numbers with many digits. An alternative and even more optimized approach is to use logarithmic calculations. Here, we leverage the property that the number of digits in a number can be determined using floor, log 10, number, plus 1. Using this property, we can directly calculate the number of digits without iterating or converting the number to a string. This method is highly efficient, with a time complexity of O, n, as logarithmic calculations are performed in constant time. The space complexity remains O1. Despite its efficiency, this approach does have some trade-offs. It assumes familiarity with logarithms and may introduce minor precision issues when working with extremely large numbers. After evaluating these approaches, we opt for the mathematical method that uses division to count digits. This approach strikes the best balance between simplicity and efficiency. While the logarithmic method is theoretically faster, it introduces potential precision concerns and may be less intuitive for some. On the other hand, the brute force method, though easier to implement, is less efficient due to the overhead of string manipulation. By using the mathematical approach, we avoid the inefficiencies of string operations while maintaining robustness. Counting digits through division is straightforward and does not rely on external libraries or complex mathematical concepts. Additionally, it avoids the potential pitfalls of precision errors that can occur in logarithmic calculations. Although slightly more intricate than brute force, this approach is practical and efficient for general use cases. The final complexity of the chosen approach is as follows. The time complexity is O, n*k, where n is the number of elements in the array and k is the number of digits in the largest number. The space complexity is O(1), as no additional memory is allocated beyond the counter used to count digits. This method achieves a good balance between clarity, efficiency, and robustness. It avoids the inefficiencies of string manipulation and the potential precision issues of logarithmic calculations, making it an optimal choice for this problem. While not the fastest in all scenarios, it is simple to implement, easy to understand, and performs well for a wide range of input sizes. The problem we're solving here is to determine how many numbers in a given array have an even number of digits. For example, if the input array is 12, 345, 2, 6, 7896, we observe that 12 and 7896 both have an even number of digits, so the output should be 2. To solve this, we will use a brute force approach and break the process into clear steps. First, we need to understand the input. We are given an array of integers, nums, and our goal is to count how many of these numbers have an even number of digits. Next, we will iterate through each number in the array, one by one, and determine the number of digits it contains. To calculate the digit count, we can convert each number into its string representation using str, number. This allows us to easily find the length of the number by using the len function, which gives us the total number of digits for that number. Alternatively, instead of converting the number to a string, we can use a mathematical approach to count the digits. This involves dividing the number by 10 repeatedly until it reduces to 0, while keeping track of the number of divisions. Once we have the digit count, we check if it is even by using the modulo operator, %. If the digit count modulo 2 equals 0, it means the number has an even number of digits, so we increment a counter that keeps track of such numbers. After processing all the numbers in the array, the final step is to return the value of this counter as the result. To summarize, here's a pseudocode representation of the algorithm. First, initialize a counter variable, even_digit_count, to 0. Then, for each number in the array, calculate its digit count and check if it is even. If it is, increment the counter. Finally, return the counter as the output. Let's walk through an example to see how this works. Suppose the input array is 12, 345, 2, 6, 7896. We start with even_digit_count set to 0. The first number is 12, which has a length of 2 digits. Since 2 is even, we increment the counter to 1. The next number is 345, which has a length of 3 digits. Since 3 is odd, we make no changes to the counter. Then, we process 2, which has a length of 1 digit, again odd, so the counter remains unchanged. Similarly, 6 has a length of 1 digit, so no change. Lastly, we process 7896, which has a length of 4 digits. Since 4 is even, we increment the counter to 2. After processing all the numbers, the final output is 2. This example highlights the simplicity of using str, number, to calculate the digit length, which avoids the need for manual digit counting. Alternatively, the mathematical division approach can also be used, where you divide the number by 10 repeatedly to count the digits, but the string-based approach is often cleaner and more intuitive. To determine whether the digit count is even, the operation length %2 == 0 is computationally efficient, as it runs in constant time. There are also several edge cases to consider. If the array is empty, we should return 0 since there are no numbers to process. For arrays with very large integers, the algorithm remains robust because Python handles large integers natively without overflow issues. Additionally, for negative numbers, the digit count calculation should ignore the negative sign, as it does not contribute to the number of digits. In terms of data structures, we are working directly with the input array nums and do not modify it. We use a single counter variable, even_digit_count, to track our result. The time complexity of the algorithm is O(n*d), where n is the number of elements in the array, and d is the number of digits in each number. Since d is typically small and logarithmic with respect to the number's size, the complexity is often approximated as O(n). The space complexity is O(1), as we only use a constant amount of additional memory. This Python solution solves the problem of finding numbers with an even number of digits in a given list. Let's break it down step by step. 1. Class definition. We define a class solution according to LeetCode's requirements for submission. 2. Method definition. A method named findNumbers is defined within the class. This method takes a single argument, nums, which is a list of integers provided as input. 3. Variable initialization. We initialize a variable even_digit_count to 0. This variable will keep track of the count of numbers that have an even number of digits. For iterating through the list, using a for loop, we iterate through each number in the list nums. For each number, we convert it to a string using str_number. This allows us to easily count the number of digits in the number by checking the length of the string using len. We then check if the length of the string representation of the number is even by calculating len str_number %2. If the result is 0, it means the number of digits is even, and we increment the even_digit_count variable by 1. 5. Returning the result. After the loop finishes, the variable even_digit_count contains the total count of numbers with an even number of digits. We return this count as the result of the method. ###edge case is handled. If the input list nums is empty, the loop will not execute, and the method will correctly return 0. Numbers with only one digit, e.g., 1, 3, are correctly ignored since their digit count is odd. Large numbers and varying input sizes are handled efficiently due to the simplicity of the len str_number operation. ###complexity. Time complexity. The solution iterates through the input list once, and for each number, it performs a constant time operation of converting to string and checking the length. Thus, the time complexity is O(n), where n is the number of elements in the input list. Space complexity. The space complexity is O(1), since no additional data structures are used apart from a single integer variable for counting. This solution is efficient, clean, and handles all edge cases gracefully, making it a robust solution to problem number 1295 on LeetCode. This is the Java implementation of LeetCode problem number 1295, find numbers with even number of digits. It mirrors the Python logic by iterating through the array and checking if the number of digits in each integer is even. Key differences include the use of Java's integer.toString method for converting numbers to strings, explicit type declarations, and the structure of the Java class. This implementation maintains the same functionality as the Python version, ensuring correctness and clarity. To solve this problem, we start by initializing a variable called even_digit_count and set it to 0. This variable will help us keep track of how many numbers in the input array have an even number of digits. Next, we iterate through the array nums. In the first iteration, the current number is 12. We convert it to a string, which gives us 12, and then measure its length. The length is 2, and since 2 is even, we increment even_digit_count by 1, making it equal to 1. For the second iteration, the number is 345. Converting it to a string gives 345, and its length is 3. Since 3 is not even, we leave even_digit_count unchanged at 1. Moving on to the third iteration, the number is 2. Converting it to a string gives 2, and its length is 1. Again, 1 is not even, so we keep even_digit_count at 1. Now, we proceed to the fourth iteration, where the current number is 6. Converting it to a string gives 6, and its length is 1. Since 1 is not even, even_digit_count remains 1. Finally, in the fifth iteration, the number is 7896. Converting it to a string gives 7896, and its length is 4. Since 4 is even, we increment even underscore digit underscore count by 1, making it equal to 2. With no more numbers left in the array, we return the value of even underscore digit underscore count, which is 2. Let's look at another example where the input array is nums equals 555, 901, 482, 1771. We again start by initializing even underscore digit underscore count to 0. In the first iteration, the number is 555. Converting it to a string gives 555, and its length is 3. Since 3 is not even underscore digit underscore count remains 0. In the second iteration, the number is 901. Converting it to a string gives 901, and its length is 3. As before, 3 is not even, so even underscore digit underscore count is still 0. In the third iteration, the number is 482. Converting it to a string gives 482, and its length is 3. Since 3 is odd, there's no change to even underscore digit underscore count, which stays at 0. In the fourth iteration, the number is 1771. Converting it to a string gives 1771, and its length is 4. Since 4 is an even number, we increment even underscore digit underscore count by 1, making it equal to 1. At this point, we've gone through all the numbers in the array, so we return the final value of even underscore digit underscore count, which is 1. Now, let's work through one more example to reinforce the solution approach. For the input array nums equals 1, 22, 333, 44, 44, we initialize even underscore digit underscore count to 0 once again. In the first iteration, the number is 1. Converting it to a string gives 1, and its length is 1. Since 1 is not even underscore digit underscore count remains 0. In the second iteration, the number is 22. Converting it to a string gives 22 foot, and its length is 2. Since 2 is an even number, we increment even underscore digit underscore count by 1, making it equal to 1. Next, in the third iteration, the number is 333. Converting it to a string gives 333, and its length is 3. Since 3 is odd, there's no change to even underscore digit underscore count, so it stays at 1. Finally, in the fourth iteration, the number is 4444. Converting it to a string gives 4444, and its length is 4. Since 4 is even, we increment even underscore digit underscore count again, bringing it to 2. With no more numbers left in the array, we return the final value of even underscore digit underscore count, which is 2. In this solution, we begin by iterating through the input array nums, which consists of n elements. The first component of the time complexity arises from this iteration, as the for loop processes each element sequentially, contributing an O(n) factor. Next, for each number in the array, we convert the integer to its string representation using the str_number function. The time it takes to perform this operation depends on the number of digits in the number, denoted as d. If all numbers have d as their maximum number of digits, this conversion step contributes O(d) for each number, and across all n elements, the total cost becomes O(n*d). Lastly, calculating the length of the string using len str_number is a constant time operation, O(1), since Python's len function is optimized for such tasks. Together, the dominant factor in the time complexity is the string conversion step, leading to an overall time complexity of O(n*d). To determine whether the length of the string representation of a number is even, the operation len str_number %2 == 0 is performed. This check is a constant time operation, contributing O(1) to the time complexity for each number. Combining all the steps, the overall time complexity is determined by the most expensive operation, the string conversion, resulting in O(n*d), where n is the number of elements in the array and d is the maximum number of digits in any number. However, if d is bounded, such as when dealing with integers up to 10⁻⁶, d can be treated as a constant, reducing the complexity to O(n). Shifting to the space complexity, we first consider auxiliary space. The variable even underscore digit underscore count is used to store the count of numbers with an even number of digits, which is a single integer, so this contributes O(1) to the space complexity. The next factor in space complexity is the temporary string created during the str_number operation. For each number, the string representation occupies space proportional to the number of digits, denoted as O(d). In the worst case, where all numbers have d digits, the temporary string requires O(d) space during each iteration. However, since only one such string exists at a time, this step does not compound across the array. Finally, the input array nums is not modified during the process and is considered part of the input, so it does not contribute to the space complexity calculation. Overall, the total space complexity is O(d), where d is the maximum number of digits in any number. If d is bounded, as in the case of integers with a fixed upper limit, the space complexity simplifies to O(1). When comparing different approaches, a naive method would involve manually dividing each number by 10 repeatedly to determine the number of digits. This approach has a time complexity of O(n*d), similar to the given solution, but it avoids creating string representations of numbers, making it more space efficient with a space complexity of O(1). On the other hand, the optimized approach provided in this solution already balances efficiency for inputs with a bounded number of digits. For scenarios involving unbounded digit sizes, further optimization could involve calculating the number of digits mathematically, such as using the math.log10 number function. This approach avoids string conversion entirely, reducing the space complexity to O(1), while maintaining the time complexity at O(n*d). Thus, the current solution strikes a practical balance between simplicity and performance for most use cases. When analyzing the best, average, and worst cases, we observe variations based on the number of digits in the input numbers. In the best case, all numbers have a small number of digits, such as 1 or 2 digits. Here, the value of d is minimal, and the complexity reduces to O(n), as the string conversion step becomes negligible. In the worst case, every number has the maximum possible number of digits, d, leading to a complexity of O(n*d). For the average case, where the number of digits is moderately distributed, the complexity falls between O(n) and O(n*d). To mathematically justify the O(n*d) complexity, we note that the string conversion step, O(d), dominates the computation for each number, and this is repeated for all n numbers. As big O focuses on the largest contributing factor, the overall complexity is determined by this dominant term, confirming the correctness of the analysis. Here, we're looking at some common mistakes that can arise while solving this problem. First, when using arithmetic division or logarithms to count the number of digits, it's easy to run into errors. For instance, using log10 might seem like a good approach, but it can fail for edge cases like log10, 1, returning 0, or when floating point inaccuracies occur. These small inaccuracies can lead to incorrect results. Another mistake is repeatedly converting numbers to strings in every iteration. While this approach feels intuitive, it adds unnecessary overhead to your solution, increasing the time complexity. Instead, mathematical approaches can be more efficient. Additionally, it's important not to overlook negative numbers. For example, in the case of -1234, the digit count should still be 4, but some solutions mistakenly account for the negative sign or discard the number entirely. Each of these errors can lead to incorrect outputs or inefficiencies, so it's crucial to address them early in your implementation. Another common pitfall is misinterpreting what it means for a number to have an even number of digits. Some solutions assume that all inputs meet this criterion without explicitly checking the parity using something like len, digits, %2 = 0. This can result in subtle bugs where numbers with odd digit counts are improperly included in the output. Additionally, failing to handle constraints properly is a frequent oversight. For example, edge cases like an empty array or numbers at the boundary of the constraints, such as 10-5, can cause runtime errors or incorrect results. Ignoring these edge cases can undermine the reliability of your solution, so taking the time to address them is essential for ensuring robustness. Now let's talk about some key insights that can help you in an interview setting. Recognizing patterns is incredibly important. Many problems in coding interviews require digit manipulation, so mastering techniques for calculating digit counts efficiently, such as using log10 or integer division, is invaluable. It's also a good idea to proactively ask the interviewer about edge cases like negative numbers, 0, or very large inputs to clarify the problem's constraints. Being aware of these edge cases can save you from common traps. Another important point is understanding the trade-offs between space and time complexity. For instance, mathematical approaches are faster but might be harder to implement, while string-based solutions are simpler but come with additional overhead. Finally, always explain your reasoning clearly. For example, if you choose a mathematical approach over string conversion, articulate why. This not only demonstrates your thought process but also shows a deeper understanding of the problem. Let's explore some related problems and alternative approaches. Problems like LeetCode number 7, reverse integer, share similarities because they also involve digit manipulation and sign handling. LeetCode number 9, palindrome number, focuses on digit determination and symmetry checks. LeetCode number 66, +1, deals with digit manipulation in arrays, while LeetCode number 258, add digits, requires efficient digit calculations. When it comes to solving this specific problem, there are two main approaches. The first is string conversion, converting the number to a string and checking its length. This method is straightforward and easy to implement, but it can be slower due to the repeated conversions, especially in loops. The second approach is mathematical, using either logarithms or repeated division to count the digits. While this method is faster and more efficient, it does require careful handling of edge cases, such as when the input is 0 or negative. Finally, there's the hybrid approach, which combines the strengths of both string conversion and mathematical methods. For instance, you could use mathematical checks for larger numbers to take advantage of their efficiency and fall back on string conversion for smaller numbers, where the overhead is less significant. This approach aims to balance simplicity and efficiency, but it may be harder to justify in an interview setting because of the added complexity. Regardless of the approach you choose, understanding the trade-offs and being able to articulate their pros and cons is key to demonstrating your problem-solving skills. Great job! We've successfully solved the problem find numbers with even number of digits and walked through its key insights. Remember to apply these techniques to similar problems and keep practicing. Thank you for watching, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!